In this video, we will see about the different structures of glucose. So, in the last video, we discussed about the Fischer structure or open structure of glucose and the reactions that proved the open structure of glucose. So, the Fischer structure of glucose is drawn as, we drew it like this: CHO, CH2OH, 1, 2, 3, 4, 5, 6. Third carbon, we have OH on left side, H on right side. So this is the Fischer structure of glucose. Now, the name given to glucose is D plus glucose. Now, what is this capital D and what is this plus? We know that plus sign indicates its optical activity. That is, plus shows that glucose is dextrorotatory in nature. So, the plus sign indicates that glucose is dextrorotatory. That means it rotates the plane polarized light to right or in clockwise direction. Now, capital D means it is a configuration given to a compound. Now, we have D and capital L configuration given to a compound. Okay, so this capital D has nothing to do with dextro or optical activity. This capital D is the configuration given to an organic compound. Same way we can give capital L also, but glucose is capital D plus and dextro D is small, but here we are going to show that dextro with a plus sign. Okay, dextro is small d. So, glucose is correctly named as D plus glucose. So, next we are going to see how to give the configuration D and L to a compound, that is how this glucose got its D configuration. So, next is how to assign D and L configuration to a compound. So, for this we take the compound glyceraldehyde. Now, the glyceraldehyde, the structure of glyceraldehyde is CHO, HOH, CH2OH. Okay, so glyceraldehyde, and this glyceraldehyde is given the name plus glyceraldehyde. Means this is dextrorotatory. The plus sign shows that it is dextrorotatory. Now, the minus glyceraldehyde is indicated like this. OH will be on this side, hydrogen on this side, and CH2OH. This is minus shows levorotatory, minus glyceraldehyde. So, to assign capital D and L configuration to a compound, we compare the structure of the compound with the structure of plus and minus glyceraldehyde. Now, all the compounds which can be correlated to plus isomer of glyceraldehyde is said to have D configuration, and those which can be correlated with the structure of minus glyceraldehyde is said to have capital L configuration. Now, for assigning the configuration of monosaccharides, that is our glucose, we consider the lowest asymmetric carbon atom. Lowest asymmetric carbon. And that lowest asymmetric carbon is taken and compared with the structure of glyceraldehyde. So, I am going to draw that Fischer structure of glucose again. The structure is CHO, CH2OH. Always number the carbon atoms. Here we have H, OH, OH, H, OH, H, OH. Now here the lowest asymmetric carbon atom is this part. Asymmetric carbon means the carbon to which 4 valencies attached or bonded are different. The 4 groups attached to the carbon is different. You can see this is the lowest asymmetric carbon atom, that is carbon number 5. It has hydrogen OH group, then 1 valence is satisfied by CHOH group and 1 valence is satisfied by CH2OH group. Okay, so you compare this with the structures of glyceraldehyde, the lowest asymmetric carbon. Now you can see that this portion, that is HOH, is comparable with plus glyceraldehyde. So the lowest asymmetric carbon atom of glucose can be compared with the structure of plus glyceraldehyde. So glucose is given capital D configuration. Okay, so always to compare the structure, we take the lowest asymmetric carbon atom of the monosaccharide and compare it with the structure of plus and minus glyceraldehyde. If that lowest asymmetric carbon atom has structure similar to plus glyceraldehyde, then that monosaccharide is given capital D configuration. If that structure is comparable with minus glyceraldehyde, it is given L configuration. So in case of glucose, the lowest asymmetric carbon atom structure can be compared with the structure of plus glyceraldehyde. So glucose is given D configuration, capital D. So D plus glucose. Okay. Now next we are going to see, so this is the Fischer structure of glucose, and now the name of glucose is D plus glucose. Now we are going to see there is another structure of glucose, that is the cyclic structure of glucose. So next, cyclic structure of glucose. So we had first the Fischer structure, open structure, and now comes the cyclic structure of glucose. The structure of glucose, there is a Fischer structure, explained most of its property, but the following reactions could not be explained by this structure. So here we have a question, enumerate the reactions of glucose which were not given by the open chain structure, or which cannot be explained by the open chain structure or Fischer structure. So there are few reactions which the open chain structure could not explain. Those reactions are, first one, despite having the aldehyde group, glucose does not give Schiff's test and it does not form hydrogen sulfide addition product with sodium bisulfite. So though aldehyde group was present, you did not get which test? Schiff's test, and also sodium bisulfite addition test. You know, these two tests are given by aldehydes, but when that open chain structure was allowed to react with these reagents, we did not get any result. Now the second test is the pentaacetate of glucose. Which is the pentaacetate of glucose? How is it produced? When glucose is treated with acetic anhydride, we get glucose pentaacetate. It does not react with hydroxylamine. You know the structure of pentaacetate of glucose. The pentaacetate of glucose is CHO, then CHO, CO, CH3, 4 times, CH2O, CO, CH3. This is the pentaacetate of glucose. You know that the CHO group is free here. Okay, but this pentaacetate of glucose did not give test with hydroxylamine. Means if this CHO group was free, we would get the product oxime when this pentaacetate was treated with hydroxylamine. So the pentaacetate of glucose does not react with hydroxylamine, indicating the absence of free aldehyde group in glucose. Now the next is, glucose is found to exist in 2 crystalline forms which are named as alpha and beta. So now it is said that glucose exists in two crystalline forms, alpha glucose and beta glucose. Now the alpha form of glucose is obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while its beta form is obtained by crystallization from hot and saturated aqueous solution at 371 Kelvin. So these are the three reactions that showed that the aldehyde group in glucose is not free. Okay, which means we have a cyclic structure for glucose. So we are going to discuss that cyclic structure. Now for that again I am going to draw the open structure. So the last reaction is the existence of glucose in two forms, alpha form and beta form. So now we have the name of glucose as alpha D plus glucose and beta D plus glucose. And this alpha D plus glucose and beta D plus glucose, they are in equilibrium with the open structure of glucose. So I am going to show the formation of a cyclic structure of glucose. For that we are going to draw the open structure first. Now the open structure of glucose is CHO. I am going to show the bond also. Then we have CH2OH. Now here we have, this is the first, second, third, fourth, fifth and sixth carbon, HOH, third carbon OH, fourth carbon HOH, fifth carbon HOH. Now to form the cyclic structure, one of the OH group may add to CHO group and form a cyclic hemiacetal structure. And in glucose, that it forms a six-membered ring in which the OH at carbon number 5, this OH, carbon number 5 is involved in ring formation. So what happens, this OH group at carbon number 5 will add to CHO group and it forms a six-membered cyclic hemiacetal structure. Okay, so I am going to show the addition of this carbon number 5, OH group at carbon number 5 to CHO group. Now the structure is, when you add that, you get the structure as C, H will remain as such, the double bond O breaks and hydrogen will add to oxygen. So here we have COH. This is our first carbon. Now on the first carbon we have CHOH. Now the next we have second carbon, we have HOH again. Then third carbon we have OHH, no changes here. Fourth carbon we have HOH. Now fifth carbon we have H, and here we have hydrogen added to oxygen, but we have this oxygen left. So that will be in the ring like this. It forms a ring. Now the sixth carbon we have CH2OH. Okay. Now again I am going to write one more structure for this, and this glucose that is obtained, that is a cyclic hemiacetal structure of glucose, is named as alpha capital D plus glucose. And we know that there are two cyclic structures, one is alpha form and the other is beta glucose. So I am going to draw the structure of beta glucose. Now when I draw the structure of beta glucose, it is same as the structure of alpha glucose, but the difference is only around the first carbon atom. In beta glucose, on the first carbon, OH group will be on left side. The rest all remains the same. So I am going to draw the structure of beta. COHH, this is the first carbon. Now we have second, third, fourth, 5 and sixth carbon. 2, 3, 4, 5. Here we have HOH, third carbon OHH, fourth carbon HOH, fifth carbon we have an oxygen linkage. Now this is our beta D plus glucose. Now I told you, if you look a glucose solution, we can see the open chain structure and the two cyclic structure which are in equilibrium. So we have to show that equilibrium here. This is in equilibrium, all three. Okay, so this is the cyclic structure of glucose, and you can see the difference between alpha D and beta D is around the first carbon atom, configuration around first carbon atom. Here we have OH group. On first carbon on left side in beta glucose. And you call these alpha and beta glucose, we have their isomers and we can call them as anomers. So example for anomers is alpha glucose and beta glucose. Now what are anomers? Anomers are isomers which differ in their configuration around first carbon atom. They are anomers. Okay, so these are the two cyclic hemiacetal structure of glucose and they differ in the configuration around first carbon atom. Now, next we have another structure of glucose, that is from this alpha and beta, or from the cyclic structure we are going to have a Haworth structure for glucose. So next, third structure is Haworth, or it's also called Pyranostructure of glucose. Now, Haworth or Pyranostructure. Why is it called a Pyranostructure? Because the six-membered cyclic structure of glucose can be called a Pyranostructure. Why? Because it can be compared with the structure of a compound called pyran. Now, pyran is a cyclic compound with one oxygen atom and 5 carbon atoms in the ring. And the structure of pyran is oxygen, this is the compound pyran. Now we can draw the Pyranostructure, or the cyclic structure of glucose can be drawn in this form, or this is also called the Haworth structure of glucose. Okay, so I am going to show the cyclic structure of glucose in the form of Pyranostructure or Haworth structure. Now for that I am going to the structure here. So we will have the Haworth structure for alpha D glucose and Haworth structure for beta D glucose. So this is the Haworth structure which I am going to draw. Haworth structure for alpha D plus glucose I am going to draw. Now you got the structure of pyranose. Pyranose is like this. It's a this is pyran. Okay, now I am going to draw the structure. Now we have oxygen, this oxygen. Now five-membered ring. Now so I am going to write first carbon we have here. I am going to mark the carbon atoms first. 1, 2, 3, 4, and the fifth carbon is here. 6th is our CH2OH group. Okay, so that is written on the top as CH2OH. This is 6th carbon, and here we have on the 5th carbon hydrogen here. So I am going to write that hydrogen down. Now on first carbon, those groups which are written on left side is written on the top. So first carbon we have on left side hydrogen, so hydrogen, and right side OH group. Second carbon hydrogen, OH group. Third carbon OH and hydrogen. Fourth carbon we have hydrogen on left side and OH group. Fifth is only hydrogen, and sixth we have CH2OH on the top. So this is the structure of Haworth structure of glucose. Now this is the structure of alpha D plus glucose. Now the name of the structure is alpha D plus glucopyranose. So you look at the cyclic structure of alpha D glucose and draw the Haworth structure for glucose. Now let's draw the Haworth structure for beta glucose. Now to draw the beta glucose Haworth structure, again we have oxygen and then draw the 5-membered ring, 1, 2, 3, 4, 5. Now you have to number the carbon atoms. So 1, 2, 3, 4, 5, and the 6th carbon is here, CH2OH, 6th carbon. Now you know the difference between alpha and beta glucose is around 1st carbon. So here in beta glucose, the Haworth structure also we have the difference at 1st carbon. 1st carbon we have OH here and hydrogen down. The rest all is same as our Haworth structure for the alpha glucose. Or look here and draw those groups coming on left side is written on the top. So HOH, then OH, H, and here HOH. And here we have one hydrogen. On the 5th carbon we have hydrogen. So that is also drawn. And now the name of this compound is beta D minus glucopyranose. Okay, so this is the Haworth structure of glucose, that is alpha D plus glucopyranose and beta D plus glucopyranose. So look at the cyclic structure of glucose and draw the Haworth structure for the glucose. So these are the 3 structures. First is Fischer structure or open structure. Second is cyclic hemiacetal structure, which is formed by the addition of OH group at 5th carbon to CHO. And the last is Haworth structure or pyranose structure of glucose. Okay, so with this we complete the structures of glucose. Thank you.